Hello everyone, I'm Umar Niazi. I'm a PhD student at Gypsy Lab, Grenoble, France. I'll present my paper with Carlos Canutas-Dewitt and Elanki Bangu on state variance estimation in large-scale network systems. What is state variance? So the motivation behind this nonlinear functional of the state vector comes from the fact that in large-scale network systems we have limited number of sensors as compared to the size of the system, and this may render the network system unobservable. Moreover, we have limited computational resources which can make the state estimation task infeasible. So in this scenario, what we do is we estimate some kind of aggregated state profiles of the system, for example, mean, which is a linear functional, and the variance, which is a non-linear functional. And these two functionals are scalar functionals. The application of aggregated state profile estimation is in traffic networks, where we want to estimate the average traffic density inside a sector and also the variance. In building thermal systems, for example, here we have a 4-room building model where we want to estimate the average mean temperature in each room and the temperature variance along the rooms. In sensor networks, we want to estimate the mean value, which is a consensus value, and we want to monitor the consensus formation through the estimation of variance. Our system is defined on a weighted digraph. That means this is an LTI system with the state matrix A having a structure that is given by graph G. And without loss of generality, we can assume that our measured states are the first M states and the unmeasured are the next N states, and N is quite large than the number of measured states. The state matrix is assumed to be Metzler. That means its off-diagonal entries are non-negative, and it is semi-stable because its eigenvalues lie in the open left half complex plane and the zero eigenvalue. That means it can be written as some diagonal matrix lambda minus a Laplacian of the graph. Our problem is to estimate the state variance, which is defined as 1 over n times the sum of the squares of the differences between unmeasured state and the average mean. In the vector form, it's written as 1 over n x2 times jn x2, where jn is a positive semi-definite, so it's some kind of a mean-centered norm of the unmeasured state, and Jn is also idempotent and symmetric. One way to solve this problem is to design a functional observer of dimension k, and we design these functions f and h such that the difference between original and estimated state variance exponentially converges to 0. However, there is a fundamental limitation, and that the dimension of the observer has to be at least n minus 1, and this comes from the fact that state variance is some kind of norm of a functional of a state, and that functional it depends on Jn, which is of rank n minus 1. So in order to estimate v here, we have to design an observer that must be at least n minus 1. It can become computationally infeasible if n is very large, where n is the number of unmeasured states. So instead of estimating state variance exponentially or asymptotically, we are interested in estimating the state variance in an approximate sense, and it is because we have limitation on the dimension of the observer. So we are given the order of the observer k, and we want to estimate the state variance approximately, and that approximation must be in some optimal sense. So first we cluster the network into k clusters, which is the dimension of the observer, and then we approximate the state variance from the average states of those clusters, and then estimate the average states and then compute the approximated state variance from those clusters. And the idea of clustering here is to identify the nodes whose state trajectories are close to each other. In part 1, we illustrate the variance approximation method, where we have in the first figure the state trajectories of unmeasured nodes, and we identify the trajectories that are close to each other. And in the next slides I will explain how to do that. And when we identify the clusters of nodes whose state trajectories are close to each other, then we can approximate these state trajectories through their average mean state. And from that average mean state, we can approximate the state variance. So here in the solid black line is the original state variance, and in the dotted black line is the approximated state variance. So in the more formal sense, we want to find K clusters such that we can approximate the unmeasured state vector with QZA, where ZA is a vector of average states. Then we can approximate state variance by replacing X2 with QZA. And then we want to minimize this distance. So from X2 minus QZA, we want to minimize that. And what we do is we write the transfer function from the input U to this output, which is the difference between X2 minus QZA. And then we minimize H2 norm of this transfer function. And this is a finite time H2 norm because our A matrix is semi-stable, is not Hurwitz. And we want to find the clustering such that this cost function is minimized. And here we have to compute a finite horizon controllability gradient, but this computation is offline because it doesn't depend on the clustering queue. The problem of clustering is an NP-hard problem. So what we design is a greedy algorithm where we initialize the clustering randomly, and then for each node we check which cluster is the best cluster that yields the minimum cost. And then we do it, after doing it for each node, we do it iteratively, and we do it until the cost is no more reduced. So we return the suboptimal clustering, and then we initialize this clustering again because the optimal solution is a suboptimal one, and it depends on the initial clustering. So we initialize randomly several times in order to achieve a better suboptimal solution. In this illustrative example, we show how the algorithm works. So basically it is identifying the clusters of nodes whose state trajectories asymptotically are close to each other. First, what we do is we project the network system on a lower dimensional state space and obtain this projected network system, which is defined on this aggregated graph. The average state observer is given by this system whose state is W, and it gives its output is the estimated average states of the clusters. And the matrices are chosen like this, and here our design matrix is V, and it depends on the clustering and system, and there we have a freedom to choose alpha, which is a scalar tuning parameter. So the ideal case of average state observer is when the average state estimation error zeta converges to zero asymptotically, and this can be characterized by three conditions. And the first condition corresponds to average observability, where we can bound the average state estimation error by some exponential, which depends on alpha, which is a tuning parameter. That means we can choose alpha as large as possible, and then we can change the rate of convergence to be arbitrarily fast. But it comes with a strict structural condition, which also depends on the system and the clustering. Okay. The second condition corresponds to detectability, where the error is bounded by some exponential, but it is no more controlled by the tuning parameter alpha. The third condition is a high gain type of condition, where we can choose alpha to be very large in order to make the error arbitrarily small. However, it may happen that your system may not satisfy these conditions because they impose strict structural constraints on the clustering and also on the system. In this case, we minimize the average state estimation error. First, we write the dynamics of the average state estimation error, which depends on this matrix R alpha. So R alpha is also influencing the average state estimation error as a state of this differential equation, and also it is influencing sigma. So we cannot choose alpha to be very large because that could also maximize this sigma, which is acting as an exogenous unknown input. And what we do is we minimize the H2 norm of the transfer function from state X to the average state estimation error. And then we define our problem is to find alpha, which is greater than 0, such that this norm is minimized, which is trace of the finite time controllability gramian of these two matrices, and subject to the constraint that R alpha Q must be Hurwitz. And then it turns out that it's a convex optimization problem, and it can be solved by a lot of algorithms. The estimated state variance can be computed through these estimated average state of the clusters, and the average state variance estimation error can be computed as the norm of this sigma, and this function, which depends on the average state estimation error. As a simulation example, we consider a linear transport system where each node I, the dynamics of each node I depends on the inflow from its in neighbors and outflow to its out neighbors plus some external inputs, and we consider the graph to be a Erdős-Renyi graph. So the example shown in the beginning was this example, and then we have these 5 clusters where the trajectories of each clusters are shown by different color, and then we approximate these trajectories through by their average mean trajectory, and then we estimate those average mean trajectory, and then from those average states we compute the estimated state variance. In conclusion, we presented a tractable methodology to estimate state variance. The future work involves generalization to higher moments, for example skewness, kurtosis, and then to reconstruct the state distribution, which is time varying. And then another future prospect is to devise a methodology to obtain optimal number of clusters, K.